Welcome to all of you for the second session of this last day of short-term training program. We have Dr. Murali. May I request Dr. Murali to present his talk?
Yes, I'm ready. Let me present now. Wait a minute. Are you able to see?
Yeah. Can you make a full screen?
Yeah. I don't know. Hide this. Let me know when I should start and.
Yeah. You can start, please.
Okay. Together. Okay. Today's talk on physics-informed machine learning surrogates for flow prediction. The scope of the presentation will be as follows. I will motivate why we are doing this during this period. I was never a fan of machine learning when I was a graduate student many years ago. Uh, Basic ideas of machine learning leading to physics informed machine learning. That is what motivated me, physics informed. And since I work in aerodynamics, I'm an aeronautical engineer and I focus in high speed, low speed, all kinds of fluid aerodynamics. I'll talk about some of the applications in applied aerodynamics, which a few of my colleagues and students, graduate students, interns, and all that, they're all listed here. Rahul, Shashank, Vinod, Wee Beng, Shida, Mohil, Ishan, and Yongdo. So I work. That's what enabled me to give this talk today because I started this foray into machine learning maybe like 2019. Because uh, I see that there is a resurgence, and so I decided to go back and see what happened. So I'm going to give you a little bit of history to motivate why some of you may consider going into this field. So in 1950, this is a timeline. 1950, you have that famous Turing test was invented, and then there was some activities going on in AI-related work in those days. And the 2 points, 1973 and 1988, when the interest actually went down the drain. So those are, in the history, it is called AI winter because the majority people have dumped it and they want to know, went on to do other things. The first thing happened in 1973 with the publication of a report called the Lighthill Report in 1973. This is our same Lighthill who made many contributions in fluid dynamics, acoustics, and so on. He basically killed the whole thing. Of course, he has his opponents who try to keep some activity alive. And then there was a resurgence. Okay, so there was some boom times started to happen. So during this period, 50 to 73, most of the AI-related work was based on a Lisp programming language, which was actually came into the scene in 1958. So a few years around there, I think 54, Fortran came into being, and so that was heavily motivating all the finite element, finite difference, and finite volume codings. So here, Why the boom time came? Because there was a development of a computer algebra software, Maxima, came into the scene in 1981, followed by MATLAB in 1984. So people started to explore some of the ideas using these softwares. These are basically, computer algebra software, symbolic programming, and so on. So there was a boom which went on until it hit the second winter, because during this period there was a lot of investment on expert systems and the fifth generation supercomputers and so on, and that all died in 1992. All right, so with that, people didn't bother so much. So interest start to, but some people keep it alive. Okay, whenever the things go wrong, not everybody abandon it. Some die-hard guys will always be there to keep the flame going. Somewhere in 1991, Python programming language came into the scene. In 1994, the message passing interface, which facilitated parallel computing, came into the scene, and that made a lot of developments in high performance computing, in high fidelity CFD, finite element, and so on, many things. In especially, I'm talking in the realm of computational engineering, which is the area where I have worked for many years. And in 2007, the NVIDIA CUDA programming language have come, and there's a resurgence. I mean, this GPU, graphical processing unit, which are actually, some chips which are used for gaming, that has been deployed for fast computing, parallelization, basically. So that led to a lot of new activity, and the AI start to resurgence in 2012. So there is a deep learning revolution which took place around 2012. And the scientific community, yeah, off and on, some guys may be doing, but real interest started coming around 2018, 2019, with the publication of this report on scientific machine learning as the way to the future. All right, so this report is available in the web. Anybody can read it and see what is in store for the next 10, 15 years. If you look at the software developments, is also helping the resurgence in AI. In 2015, you had Keras, 2017 TensorFlow, 2012 Julia, and 2019 the Julia machine language called Flux. All these make programming, AI, networks, and all that a breeze. So there are a lot of developments in softwares and so on. Sometime around 2008, you had the only the flood 2008, which is the open neural network that is written in C++, that is also available. Some people in Europe uses it. So this is the state of affairs currently. We are around this area, and so you can go and look at all these things and see what is happening. So essential tools for machine learning are all these things: Python, TensorFlow, Julia, Keras, and this is what all the young fellows are using. Myself, I'm all familiar with Fortran. I grew up in that age, but you need to pick up if you want to do things differently. The first time I saw anything about artificial intelligence was through this report when I was a research fellow working in NASA Ames, and somebody was writing a topic on computational aerodynamics and artificial intelligence. Now, computational aerodynamics was actually developing during that period. Jameson, finite volume, Ames research codes, and all that. So in this report by Mehta and Paul Cutler, all right, it was presented as an AIAA paper. They talk about the idealized expert system for computational aerodynamics. Okay, so this is actually the thought process from the olden way of thinking. They think that you have to do a lot of things. You need knowledge. You need so this is a flow chart, idealize knowledge, controller, whatever. Okay. So they want to. So these are some of the things the report says. I want to build expert system in CFD. I need things for mesh generation, numerical methods, and so on. So these are some basic things like Spider expert system in grid generation, optimizer, and that all led to some intelligent front end to Phoenix CFD, which is Phoenix is basically the first commercial software written by Brian Spalding. And with that, this whole thing actually died. Okay, expert system, that was the thinking at that time. Now, over the last couple of years, there is a new way of thinking in this field. So we look at the forward problem in our field. We have a problem to solve, say like a flow past a body. We do high fidelity computing or rich experimental PIV. Okay, it's very costly experiment. The computing is basically I have a program, which codes, methods and all that to solve CFD equations. And then I give input data, the geometry, CAD files, and boundary conditions, and then I get some output. After some time, you'll get some solutions. So this is a high fidelity output. Now you can actually do an inverse problem. That is what is widely applied in applied aerodynamics from year 2000 onwards. You take these high fidelity results and do a model order reduction like ROM, POD, DMD, SVD, and so on. So if you construct a low order prediction model, you can put the input and you can predict output much faster. Okay, so that is also one of the ways people are developing surrogates to predict aerodynamic loads, flow fields, and so on. So this reduced order model, like I said earlier in the talk this afternoon, that there are many things. We just only covered one aspect, the pod. There is basically intrusive reduced order model and non-intrusive reduced order model. Intrusive meaning the governing equations are actually projected on a reduced basis, requiring, and this one will involve in a whole lot of changes to be made to the flow solver. So, and the other one is non-intrusive reduced order model. That is basically based on data-driven approaches, and it requires a minor change to be made to the flow solver. So this is the state. So model order reduction, this is what I don't have to talk about it. You have seen this slide, so I don't have to elaborate. Stage 2 is what we are interested in, is using the artificial neural network. Now, there are many ways to do it. The thing that I'm looking at is the standard ANN, where you have a deep neural, deep layer, many layered networks of neurons. So the first layer there, that is my input, and that is my output. And inside I can have an architecture of neurons. Okay, they're all connected. And so network, I will have to train this network with data. So once trained, I can just use that to predict. So basically, your machine learning tool is a program. So just put arbitrary input and output, and this is a very, very fast way to get your predictions, much faster than even MOR. But how reliable it is, these are questions people ask. Basically because physics-oriented guys don't care about this kind of things. So the black box ANN for training and prediction, that is what So if you look at a artificial neural network, what goes on inside? These are the inputs. Like for example, I can give X, Y, Z, and all the velocity, everything. And this is my flow field. Sorry, X, Y, Z, and T. And here I can put flow variables, rho, U, whatever. Now, if I already have some data from high fidelity, I can train because I know that at these locations, I know what is my velocity. So I can train them for some parameter. And so, what is this neuron here? If I look at a neuron is a summing device. I'm putting inputs. These are my inputs, and they are actually multiplied by some weights, which I do not know. The weights, weight multiplied by my input is actually summed up here, and there's some bias. The bias can actually be absorbed into the weighting matrix also. So it's a very simple thing, all right? This is based on a very old idea, MLP, right from so long ago. And whatever you sum here, you put it in an activation function. And if you look, there are plenty of activation functions in the literature. And of that, some of the most useful ones are shown here: sigmoid, hyperbolic tan, ReLU, leaky, and so on. Okay. So you take this sum and put inside this function, and that is this function here, sigma, right? So the output will be just the function acting on this summed weights. So this is actually WT transpose of the weight times the input. Okay. Now my idea is to teach this network so that I can find the optimal values of the weights, uh, you know, by doing some back propagation or optimization routine to minimize the error between predicted values and expected values. So when I do that, then I have some confidence because then I can put in anything and get some answers, and then you want to see. So that is the whole idea of the neural network. Okay, and that's used very nicely in many fields: facial recognition, speech, whatever. There's so many things people have done. So that is what all about. There's some input X, and there is an output Y, and the Y, the function form will look something like this. Okay, it's a function because you're summing up. Each neuron has a weight, has a bias. You add up everything. Y is equal to this. Okay, so inside here, this is the input here, X, and this matrix of weights and biases is what you should find, and that is obtained by optimizing the MSE, which is the mean square error between the predicted output and expected output, which is the ground truth. And so there are optimizers. It's a root, like something like a mean square error, and then you optimize. You need to find new values of W. This is something like steepest gradient. This alpha here will be the rate of learning, and you have to do this. So once you come here, you have to do this thing, and then you propagate back to everywhere, and then you continue until this mean square error, reaches a desired level, like which you prescribe. That is in a nutshell what ANN does. Idea is not new; it has been there. It's just as newcomers like myself, I need to learn a little bit. The thing that set me in motion into this area is basically the great work done by Brown University Crunch X group, led by Professor Korniadakis. One of their students did or research fellows by the name of Dr. Marisi developed this physics-informed neural network. So basically, what is happening if you look at this one here? Okay, here there is X, Y, and T, which is the spatial and temporal could be your coordinates of the mesh, and then you know that at that point I know what is my U component, V component, and pressure. Okay, so you put the hidden layers, the number of neurons in the hidden layers, the number of layers are all parameters with which you decide. You can have one layer, one deep layer, that is called extreme machine learning. That kind of architecture is there as well. So now you train, you have some data, you have some maybe experiment data or whatever. And then what you do is, when you predict, when you are doing this, you have an MSC coming from there. That is basically the uh, loss function. Now you take these values, outputs, and put it inside the governing equations of the flow. Because this is a incompressible flow, you take the values and put it here. This is the continuity equation, this is the x momentum, and the y momentum. This is all scaled up. Okay, this ST is the Strohal number. You can take it as one for certain cases. Certain cases you have to look at the frequency of vortex shedding and decide what it is. So when you put these values inside here, you won't get zero. These equations must be satisfied. These all go to zero, because that's the PDEs for the flow. So you'll have an error. You take the square of the error, that is called the residual physics-based loss. I put a lambda here. You can, in most of the papers, lambda is usually 1, but this is a parameter you can play around with. And then you do this. You take this physics-based loss and add it to the network loss, and that will be the total pin loss, and that is what you're going to optimize in the back propagation. That is the physics-based neural network, and this, I think, is changing the way a lot of things are happening in fluid mechanics and various other fields. Okay, so that's what got me into this field. I had to do a lot of reading up, and so on. And you have to interest some young people, to do the hard work. So that's how we get. So the physics base is looking like this. Okay, so this is the uninformed ANN, because this is just data driven. Input, output, and some prediction. But that output is being informed by the governing equations of the process you're trying to model. So that is what physics-informed learning and training is all about. So to illustrate how this is done, I give you some examples from some of the work we have been doing. So we started very simple with 2 interns from IIT Madras in summer 2019, I would say, 2019 summer. So I posed them this problem. This is a 1D nozzle flow. Okay, this is a compressible flow in a nozzle. If you look, if I change the back pressure, there will be compressible flow inside this diverging portion, and there will be a shock. So if I change this back pressure, the shock will have different strength, and so on. So this is the unsteady equation. This is the compressible flow, 1D compressible flow. This is unsteady. The steady state, I throw away all the temporal terms, and you basically end up with this. So we need to know, for a given back pressure, what is the shock strength and where is it located. Okay, you can do a CFD and find out. So we can do some the data you can generate from CFD or even analytical method. You put it inside here, back pressure and X, some functions here, and this is my output, rho, U, P, and E. And these are my governing equations. You can add, and then the net loss you can find. You take this output and put inside here, and you do the back propagation. So you have to, again, concatenate the data set just like ROM, so you have a big mother data set generated at 100 nodes along the X direction. It will generate spatial data corresponding to 27 different back pressures. For the mother data set, will consist of 4 two-dimensional matrices of 127, basically spatial and back pressure corresponding to the density, pressure, velocity, specific energy. Matrices are flattened to obtain 4 vectors of this size, each for the 4 output variables. Okay, then the training data is generated by randomly selecting, say, 27 or 1%. You can change this number, right? From data vectors, the 4 data vectors. Testing data is generated by taking this back.
Is there any problem from your side, Dr. Murli? We can't hear you.
I think he has an issue with his network.
Yeah, it seems like. Thanks. There seems to be some network issue from Dr. Murli's side. Uh, Please stay online. We'll shortly get connected with him. Dr. Rao,
Yes.
shall we do some little change in the sense because it's taking too much time?
Yes.
You can start with your presentation,
Okay.
and if Dr. Murli joins, then we'll ask him to present.
Okay. Sure. Sure. We'll do that. Okay. Let me start sharing my screen. Is Dr. Murli back?
No, I think so.
No? Okay.
No,
Okay.
no, no.
Okay. I'll continue. Okay. Am I full screen? Can you hear me?
Yeah.
So we are on full screen and we can hear you, sir.
Okay. Okay. Just to let you know, they are doing some digging around the office here. So you never know when the internet and power will get cut off or come back on. So I have organized 3 separate internet connections. So, but it'll take me some time to switch between them if I lose one of them. So just to let you know that in advance. Okay, so I think we are in the middle of an interesting presentation from Murali, and I really hope that we'll be able to get that back pretty soon. But in the meantime, we had actually coordinated each other so that we would not overlap. So I had removed certain topics from my presentation so that it would not be a duplicate of what he had. But so again, bear with me. Then certain points I'll have to explain a little bit more. If he's not back online. So basically, you can see from the title of my talk that I'm trying to keep it as simple as I could possibly manage. Given that I think most of the audience probably don't have a background in machine learning. Okay, so but you can see neural networks have become quite popular, and even you have books saying neural network for babies. So I hope I'll be able to bring it, so that we are all clear about where we are heading. Okay, so what is the goal of my talk? I think I'm very clear about this talk. I hope to persuade at least some of you to work in this area. Okay, or failing that, I hope that at least some of you will incorporate the physics-informed neural network into your applications. So that is the central goal of my talk, and I'm focusing my talk around that. Okay, and specifically, if you do use neural networks and machine learning in general, but specifically neural networks, please do use neural networks which incorporate physical principles or engineering domain knowledge, and not just a purely data fitting approach. And my third point is, for those of you who may like to get started in this area, one slide on how we can get started, and 1 or 2 links. For that. So these are the 3 main items that I want to convey in my talk today. So outline basics of machine learning, certain principles which carry over to any machine learning model, not just neural networks, and critically how to handle data. For that, Dr. Murali also already mentioned about training and testing data, so I'll elaborate a little bit on that, because that basically makes a difference between a good machine learning model and one that doesn't do a good job. Some of you may have read in the news about machine learning models that get trained in a wrong way, that exhibit racist or sexist biases, and in general fail catastrophically, under certain circumstances. So the main way to prevent all that is, number one, of course, to incorporate domain information into that. But at the same time, you have to handle the data requirements very methodically and very carefully. I'll now expand a little bit on neural network basics, and then going beyond purely fitting of data, how to proceed with domain-informed machine learning, and specifically physics-informed neural networks, which I will refer to as the PIN. And one or two case studies and one slide on how to get started with machine learning in CFD. Okay, so first of all, what is machine learning? I think there was a 1959 definition by Arthur Samuel, a fairly well-known scientist in this area. A field of study that gives computers the ability to learn without being explicitly programmed. And a more mathematical definition by Tom Mitchell in 1997, again, author of a couple of famous books on machine learning. A computer program is said to learn from experience E with respect to some task T and some performance measure P if its performance improves with experience. So basically there are a couple of concepts going into it. One is experience, which basically means your data and any other information you may want to throw at it. And it's being trained for a specific task or a specific set of tasks. Okay. And you also need to have a well-defined performance measure to say whether it does a good job or not. Okay. And that metric, you need a single metric, and that metric should keep improving as as you train it on more and more data. So you know that I think machine learning already plays a very important role in our lives. Handwriting recognition, even in your mobile devices, image recognition, your photos of you and your friends get tagged in Facebook and all that. And in more serious applications, you have medical imaging. You know that a lot of medical images are now at least partially interpreted by machine learning, specifically neural network algorithms. Video processing, speech recognition, natural language recognition, and so on. And in engineering, it can lead to improved analysis speed and accuracy. And you can also use it for things like fast detection of faults and diagnosis. Especially now we have much cheaper and more common sensors. So a lot of field data can be sensed. You can instrument our products with very cheap sensors, which will bring in a lot of data from the field while the device is still operating. And faults and other diagnostic information can be processed right on the device itself through via machine learning and specifically via neural network. And more recently, over the last two years or so, fast approximate solution of differential equations, which is the thing that is really of interest to us in this setting. Machine learning is very good. I'll abbreviate it as ML from now on. It's very good for very complex tasks. Okay. It is very good at extracting relationships for performing these complex tasks. Specifically, if you have an image and you want to see whether it's that of a cat or a dog or a computer or whatever, it's very difficult to write a deterministic computer program with a lot of logical rules and if-then-else statements that can do a good job at that. However, machine learning is very good at learning how to do such type of complex tasks. However, the flip side is it needs lots of data, lots and lots of data, which was really one of the bottlenecks all these decades. Dr. Murali talked about the AI winter, And one of the main reason is data was not so large in amount, and also the computing horsepower to process all these data and have the neural networks learn from data was not good enough. But since the last 8-10 years, that situation has been improving radically. So ML, machine learning, is very good at extracting relationships and rules from data, and specifically big data. The bigger the data, the better it is typically. And the models are created and generated and are data driven. And what you do is you have some model parameters. So for example, if you think of linear regression, you have two parameters if you want to fit a straight line to data. Similarly, neural networks, which basically fit a nonlinear function to your data, have many parameters. That depends on the number of neurons, number of layers, and so on. So you fit the model parameters by minimizing a cost function or an objective function, or by maximizing a reward function. So in the context of fluid flow and heat transfer and all those things, what is its benefit to us? And what are the problems associated with that? Number one, we know it's very expensive and time consuming to measure lots of data. Especially if you want to do various experiments in different settings, sometimes it is almost impossible to gather the kind of high quality experimental data that you need. So in this case, how do we train a neural network to do a good job in CFD if you don't have a lot of DNS data or experimental data, high quality? So therefore, we want to incorporate domain knowledge, or specifically the Navier-Stokes equations, into the neural network. And how do we go about doing that? Now, a few definitions. I would like to give you a few definitions before we really proceed to neural networks. One is supervised learning. Supervised learning is when the data for training or fitting a model also comes with known correct answers. So you have some data and you know the questions to be asked, and given the inputs, you also know the correct outputs. So if the neural network or machine learning model spits out the wrong output, you can quantify the error by means of your cost function. Okay. So supervised learning fits the machine learning model on known inputs and known outputs. And the loss function is typically a measure of the error in the model. By how much does the model output deviate from the correct answer? And you try to minimize the error by changing the model parameters. Then once you have finished your training and evaluation and testing of the model, you can deploy the model in a realistic setting, and it can be used for making predictions. In unsupervised learning, however, the data does not come with the correct answer or labels attached to it. Okay. Typically, for example, you want to, Dr. Murali talked about the proper orthogonal decomposition or DMD and so on. So you can think of those as some sort of unsupervised learning. You did not attach any label to that data. Instead, the machine learning is used to analyze or find patterns in the data, and typically used for things like model order reduction, clustering, compression of data, and so on. There are other things like reinforcement learning. I'll not get into that here. Instead, I'll talk about two broad classes of supervised training. First is regression type models, where the model outputs are continuous variables. For example, velocity, temperature, pressure, and so on. I'm sticking to examples in the context of fluid mechanics and CFD. So you have things like velocity, temperature, and so on, which, if you want to predict those things using your machine learning model, that basically comes under regression problem. The typical example of regression is your linear regression, which probably all of you are familiar with. Now, there's also another set of problems called classification, where you want to identify certain discrete values. Where you want your model outputs for discrete values. One interesting, nice example is I think yesterday Dr. Dirbule talked about multi-phase flow regime classification, based on pictures, and also one option is to use machine learning to do the actual regime classification. For example, you could have bubbly flow, slug flow, churn flow, annular flow, and so on. So this type of thing is not really a continuous variable, but there are discrete classes of flows. So this is a classification problem. Another simpler example is whether you want to classify the flow as laminar or turbulent. And neural networks can be used for both types of problems. Okay. Now I'll just mention a few things about the data. It all starts with data. Some books refer to data as examples in case you read up more on the subject. And you will also come across a terminology called IID. And it basically stands for independent and identically distributed data. So this is a statistical measure, and it's assumed that your data is identically distributed, and comes from, and they are not correlated with each other. If it is well correlated, then probably some of the data is redundant and your model does not learn anything new from that. If the data is not identically distributed, then your training data will differ from your test data, and it will also differ from the data you use in the field. So naturally, your network, which is trained on one type of data, for example, if you train your neural network on laminar flows only, then in the field, if it encounters a turbulent flow, it's not going to do a good job of predicting the values. Okay, so you have to make sure that if you're training a neural network to predict both laminar and turbulent flow, your training example should come from both laminar and turbulent flow. And furthermore, preferably they should be distributed such that your field data, suppose it encounters for 5 readings, it encounters 3 examples of turbulent flow and 2 of laminar flow in the field, then your training data also should be distributed in a similar way, for best results. And the most important thing is how you split your data into training, validation, and test splits. And also, why not just 2 splits, training and test? Why training, validation, and test splits? I'll get into that. Okay. Training data is the subset of data used to fit your model. By model, I mean any machine learning model, including neural networks. So you have to decide on a training, validation, and test split. And specifically when it comes to test data, you hold out a certain percentage of your examples or data as test data, and don't even look at it until all your models are ready for testing. Okay. Specifically, your model should never be seeing any test data until until it's almost ready to be. The next stage after testing is deployment. Okay. Typically, what I do is 80% for training, 10% for validation, and 10% for test data. And I usually mix up all my data and then do a random sampling, shuffle my data and do a random sampling to get these, so that I make sure my data is identically distributed in IID. In certain cases, I will also do stratified sampling. If I have different classes of flows, I want to make sure that I don't bias my training towards one particular set of examples. For example, if I want to train for flow around a cylinder, circular cylinder, and flow around a square cylinder, and I have only 10 examples of square cylinder and 100 examples for circular cylinder, then if I mix up my data and then do a random sampling, I will not get too many examples of my square cylinder because there are so few of those. So then in that case, I have to do a stratified sampling to make sure that I do sample a statistical number of cases from the rarer instances of my data. Okay. So what is the difference between validation and test data? Okay. So as I mentioned earlier, you take your test data by a random sample or a stratified sampling and keep it aside until all your models are tested. I mean, have been developed and are ready for testing. But in the process of training, you also want to do a separate training and validation split. Okay, and what exactly does that mean? A trained model should be validated on data that it has not seen before. This is validation data. Okay, so I take a model, I take my data, I split it into training and validation split. I do the training and then I test it on my validation set, and then see what is the accuracy that I get. Okay, so I'm interested in getting the best accuracy on the validation data, and then I keep that model aside. But typically what we do, we never stick with just one model. Okay, we train a whole series of models. Okay, and why do we do that? We have something called hyperparameter tuning. That is, if you look at it in the neural network, such as what Dr. Murali showed, you can have the parameters of a network, which are basically the weights. And these weights are basically differentiable. Your cost function or loss function is differentiable with respect to the weights. So you can train your weights on that. But there are also other parameters like number of layers, number of neurons, and so on, which are not differentiable with respect to your loss function. So these you have to change by some other means, maybe manually or by some software like auto ML or something. And then you have a whole series of different models. Okay, to come across a simpler example, suppose I want to fit a straight line to my data using the least squares method, and then I want to, instead of just fitting a straight line, suppose I want to fit a series of polynomials, say straight line, quadratic, cubic, and so on, to see which gives the best result. Then that is basically hyperparameters, because I have different terms in my polynomial, right, of different degree. So I test all that, I train all that with its own training and validation data. And then I now have a collection of models or an ensemble of models which work together to give better accuracy than any one model alone. Now we want to test all these models on data that none of them have ever seen before, right? I want to see what is the best model, what is the individual performance of each model, and so on. And that is the use of the test data. So this is a standard protocol that should be followed as per modern best practices. You should split into 3 parts. Okay. And another alternative is something called k-fold cross-validation. In my opinion, it's more useful for small data, where the data is partitioned into k groups, and each group is successively used as the holdout or the validation set. And suppose I'm training k different models, I will fit the ith model by retaining the ith group as the validation data and the rest of the group as the training data. Okay. So I hold out just one part of it and train a model. Then the next model I train, hold out some other data for that. Okay. So basically, some concepts. Oops. Some disturbance here.
Murli sir is back, I think.
Okay, I'll stop here then. And
Dr. Murli? Dr. Murli? I think Dr. Rao, you please continue. We'll take him. Dr. Rao?
Okay, can you see my screen?
Yeah, yeah.
Okay, okay, good, good. Okay, so basically, some concepts. So machine learning is inductive. By inductive, I mean models are fed or learn using some specific examples. You must have all seen the principle of induction in math courses. So basically, using specific examples, and then we expect the models to generalize to unseen data. Okay, both validation data, test data, and after deploying in the field, field data. Okay. And generalization, you will see these terms typically used in machine learning papers, so I'm presenting them. The model must perform with reasonable accuracy on data it has never seen before. Okay. It must perform well, and very importantly, it must perform well on data it receives in the field after you deploy the model. And you will see another concept called overfitting, when a model performs very well on training data, but not on your validation data. So these are all things that you'll see in papers. And the typical cost functions or loss functions that you use for training your data is usually mean squared error. You must be familiar with this from fitting least squares straight lines to data. So it's the same concept. Sometimes you also use the mean absolute error, which is basically the absolute error of the difference between the correct examples and correct output and your model's predicted output. Okay. The mean absolute error, there are some mathematical proofs that it gives a sparser parameter space than the mean squared error. And for classification problems, you typically use various forms of the cross entropy losses. I will not go into that here in this one because of time constraints. Now I will get to artificial neural networks. Okay. This basically complements now what Dr. Murali started off with. Let us now just look at a single neuron and what is the mathematical model behind it. So reading the model from left to right, you have a collection of inputs to your neuron. Okay, x1, x2, x3, so on up to xn. These inputs are multiplied by weights, respective weights, w1, w2, w3, and so on, and they are all summed up, which is the meaning of that sigma, capital sigma symbol there. It's a weighted sum of inputs. Some literature refers to it as also linear activations. Okay, so the summation is in that red colored sigma symbol there. This linear activation now goes through a nonlinear transfer function, also called the activation functions. Okay, function, and then that gives you the output of that particular neuron. Okay, so in mathematical terms, you have the linear activation, which is z equals summation of xi dotted with wi. And these are typically written as vector dot products. Okay, and the final output is a nonlinear function of the weighted sum of the inputs. Okay, this nonlinear function is absolutely essential for the neural network to be able to capture any arbitrary nonlinear function. If you had a linear function, then the entire thing can be just written as a linear matrix multiplication, and then the network would not be able to capture any nonlinearities. Okay. So you go to what is called a multi-layer perceptron. You have, I'm showing you a schematic of a artificial neural network, specifically a multi-layer perceptron with one input layer, a hidden layer, and an output layer. Okay, this forms a computational graph, and in literature you will also see deep neural networks, which are basically neural networks. Technically, they are defined as neural networks with more than one hidden layer. But if you go past one hidden layer, typically you have several hidden layers. So these are called deep neural networks. Okay. So we just saw the equations for one neuron. So now when you put all these neurons together, operating both, working together in one layer as well as in several layers, a collection of neurons working together is a very powerful function approximator, and it is that property that we'll be using in our subsequent work. Okay. So as a universal approximator, you will find that neurons are generally arranged in layers. Deep neural networks have many layers. Even as multi-layer perceptron with a single hidden layer can theoretically approximate a continuous function with any arbitrarily specified accuracy. So that is the mathematical property. It has been proven. And if it and under certain conditions, it can also approximate piecewise differentiable functions. Okay, and this result was proved by Hornick in 1990. I'm citing references as I come across them right in the slide itself. Universal approximation of an unknown mapping and its derivative. So it can approximate both a mapping, both functions and their derivatives. Okay. So if you have smooth activation functions, then neural networks are not only good functional approximators but also differentiable functions. Okay. Here I am showing different activation functions. You can use hyperbolic tan or the sigmoid function, and each layer gives its own composition of functions. So if you have, let's say, 3 layers, so it's basically function of the activation. So you can see, you can use the sigmoid or the hyperbolic tan or rectified linear unit and so on. Just keep in mind that the rectified linear unit and the leaky RULUs, they are not infinitely differentiable. So normally I do not use them when trying to fit CFD results. Okay, because after one differentiation, they become constant. Second derivative is 0, so I cannot represent my viscous terms. So I don't use those two activations. I use activations that are infinitely differentiable, like sigmoid, tan H, squash, and so on. Okay. Okay. I think I'll go over this very quickly. So you have the model fitting is done by an optimization procedure that minimizes a cost function. It's basically some variant of gradient descent or some momentum principle. And as you see, the neural network forms a computational graph, and computational graphs can be differentiated by using the chain rule of differential calculus. So you go backwards along the network, putting up the sums and products of the gradients, and then you get the complete derivative of the neural network or derivative of the output with respect to the inputs and so on. I'm not going into this in detail because these have also already been implemented in all the popular open source frameworks like TensorFlow, PyTorch, and OpenNN, and so on. So I would just say that for those who are getting started in this, just use the facilities of backpropagation and so on provided by the frameworks rather than writing your own, unless you specifically want to modify them, the behavior for some reason. Okay. And the cost function, I already mentioned the mean square error, and to that we typically add other regularization terms. The regularization can also include the actual weights. We want to sort of organize the weights and parameters learned by the model from getting too large. So you can also add a certain penalty. You can also add a penalty on the magnitudes of these parameters and weights. And to that, in CFD, for CFD purposes or for differential equation purposes, we will also add the residual of the governing equations. It's not necessary that you will only fit differential equations. Even algebraic equations you can write in the form of fx equals 0. So any error will show up as a residual which can be minimized. Okay. So regularization means both penalty on the parameters of the model as well as the residuals of the equations that you're solving. Okay. Now, at least to my knowledge, this was one of the first work in Lagares was one of the primary work in solving differential equations using an artificial neural network. And he used the property that it's a universal approximator, continuous differentiable, and it's a closed analytic form, which you don't get when you do CFD using finite difference or finite volume. You get a ton of numbers out of it, but you never get a closed analytic form. A neural network is a closed analytic form, And he used the collocation method, which is by far the most popular method even today. A collocation, and I've cited the reference. I've given the full reference for Lagares' work. So as you can see, given the number of citations Lagares' work had, it is actually surprising that this did not actually pick up 20 years ago. It had to wait till 2017 or 2018 to become popular. So I guess everything has its time. Okay, so what is this method that Lagares used? He used the collocation method, which basically consists of scattering a large number of points in your domain, including some on your boundary, and you have a differential equation dy dt or whatever is a function of t and y, and I've written it in the residual form so that so if y is to be approximated by a neural network to an arbitrary degree of accuracy, then I write y of t is neural network of t. The residual of the, if I substitute my neural network into my Gaoni equation, I get a residual because I've not trained my neural network. So since I've not trained my neural network, it's not going to give me an accurate result. There's going to be an error, which is my residual. So the residual is evaluated at the discrete collocation points, and then I put that into my cost function or loss function and use gradient descent and variance thereof, back propagation and so on. I just put in my, of course, there were no frameworks in Lagares' time, so he had to write all the codes himself. But now we have modern frameworks which can do the job for you. So what took him probably months together, you can probably finish in one afternoon. So I write the equation in residual form and I minimize the residuals using my cost function or loss function. If I can get my process to converge, then my residuals are small, preferably to within machine 0. Then I have a very good approximation to y of t using my neural network, and simultaneously I can also get my derivatives to any order that I want. So now you can see the power in a name. Lagares' method never really became very popular. At least I think you and I probably never heard of it, and it became only popular when Karnadakis and his group at Brown University gave it the very catchy name of the physics-informed neural network. And I think that's the power of a name that managed to convey the idea to engineers and scientists. Okay, so the physics-informed neural network is basically adding one more operation on top of a standard neural network. The neural network can be anything. It can take as inputs my boundary condition and my fluid properties and so on, and it predicts as outputs all my field variables at all the x and y points that I want. And then what do? I pass it through the governing equations, and note that I have the differential or the strong form of my governing equations because I'm still using a collocation method. Okay, so I evaluate it at all the collocation points and I add them up and then put it in my cost function along, and then so now you have two ways of training network. You can either train it to purely on the governing equations, or if you already have some data from measurements and experiments, you can add that into a mix. And if you have some data from high fidelity CFD simulations like LES, DNS, and so on, or even a RANS, but mesh independent RANS solutions, so that also can be thrown into the mix. So you can train on results from high fidelity CFD results, good quality experimental data, and also teach it to honor the strong form of the governing equations. Okay, so we say that it can learn from the data and has knowledge of the physics, and so that is the power of the physics informed neural network. And I think this will become one more method in CFD along with finite volume, finite element, and finite difference. I think this is going to become that way. And what are the advantages of the PIN, the physics informed neural network? As engineers, I think we all like to work with stuff that we can understand, and we do not really trust black boxes. Okay, so the explainability of the results is very important for most of us, especially if you're a designer and you are designing a new product. You are very cautious and conservative about adopting new methods and new technologies until they are proven, right? So it gives you better confidence in the result. And my own opinion is it is much more robust when evaluated outside its training data. I think given the nature of fluid flow, we will never find enough data to train a neural network for all the possible combinations of circumstances that can happen. And it is inevitable that in the field, it will be exposed to inputs that are outside the range of its training. So in which case, at the very least, you will get a warning that your results could be off, right? So it works with small data. It can work with no data, as proved by Lagares's paper. So in which case, it can be viewed as a meshless collocation method in the strong form for solving the Navier-Stokes equations. Okay, so we come to the physics informed neural network by Racy and others, 2019 paper in I think JCP, physics informed neural network. So basically in that paper they solved for Burger's equation and for the Schrodinger equation in quantum mechanics, and a couple of other one-dimensional governing equations, and also solve for inverse problems. So basically inverse problems in the sense that say suppose some property is not known. For example, the viscosity of your fluid is not known with good accuracy. So you put in a term which you put in the viscosity also as an unknown parameter into your neural network, and it finds its way then into the loss function, and the loss function is minimized with respect to not only the input variables but also your the parameters of your governing equation like viscosity or any unknown source terms and so on. So then you solve for both of those at the same time, and this is especially useful if you have experimental measurements and you want to back out, you want to do parameter estimation. So it's very useful for that. The next paper that I want to cite is one by Professor Balaji Srinivasan at IIT Madras and his students in mechanical engineering. They devised a distributed physics informed neural network. So what that means is they did the equivalent of domain decomposition, or chopped up the domain into small cells in the spirit of the finite volume method, and then they put a separate neural network in each subdomain, and then they modified the loss cost function to enforce continuity of results between the different subdomains up to I think the first derivative, and then they minimize the whole cost function together. So that was a very novel paper, I think first of its kind also. And this is described in the NPTEL course by on machine learning, part of which was taught by Dr. Balaji Srinivasan. So that's a very nice course, and he has talked about CFD and also the distributed physics-informed neural network. A third approach that I have seen is modifying a layer activation function to satisfy the constraints like governing equations and so on. But they went one step further. We know that the governing physically there are certain constraints to be imposed on the solution too. For example, your temperature should be always positive. Negative temperature, negative absolute temperature is basically a junk result, right? Likewise, negative values of your turbulent kinetic energy or species concentration, those are also physically wrong and could damage the complete solution. So these people devised activation layers with special activation layers which always enforce some of these inequality and equality constraints in the neural network. So this is also a paper that is very well worth going into for this purpose. So this is basically a recap of what I was saying here. It's a physics-informed neural network was coined by Racy and his group. Kanadak's group in 2019. And the loss function basically contains contribution from training data. The second key aspect is contribution from boundary conditions. Okay. Then contribution from the residual of the governing equations, and then other regularization terms. Now I want to draw your attention here to the second term, which is contribution from the boundary conditions. In Racy's approach, I'm sorry I didn't prepare separate slides for this. I was hoping Dr. Murali would be able to, will be able to, but I just want to mention that since he seems to be having network issues. Racy introduced, when you give inputs to a neural network, there is no guarantee that it will know what your boundary conditions are, right? So you have to make it learn the boundary conditions too. And one way to do that is to have it also output the boundary conditions, and then any deviation from the actual boundary conditions are penalized in the loss function. Now the thing with this approach is it's a minimization procedure, so your boundary conditions may be satisfied to some arbitrary degree of accuracy, but never exact. Okay. Now this is different from the procedure adopted by Lagares, which I showed you in the previous couple of slides. There he splits the solution of the governing equations into a particular solution and a general solution, a homogeneous part. The homogeneous part is devised by the, is output by a neural network and satisfies the governing equation. The particular part always satisfies the boundary conditions exactly. So the solution, the form of Lagares solution by construction always satisfies the Dirichlet boundary conditions, but probably not the Neumann conditions, but the Dirichlet boundary conditions. In Racy's approach, both Dirichlet and Neumann conditions are satisfied via minimizing the loss term. So you will never get an exact satisfaction of the boundary condition. And they still use the collocation method. Now let me briefly touch upon various applications. My hope here is to show you that people are already, most of these papers came out in the last 2 years, including, there was an explosion of research during this pandemic. So I think people had a lot of time on their hands to do more research. A lot of papers came out in 2020 also. Yeah, so I just want to show you all the diverse areas of fluid flow and structural dynamics and that it has been applied to. So I'll just give you references for various things. So pins have been used in turbulent combustion, multi-phase flows, as well as structures and structural dynamics. So not all of these are pins actually. The first one is not a physics-informed network. The second one is a physics-informed one, and it also incorporates, the progress variable in reactive flows. And the third one is basically, I think, structural dynamics paper. So basically, it's applicable. Oh yeah, one more item that I want to mention is the first reference cites convolutional neural networks, which I think will be covered in more detail by Dr. Murali, which is why I didn't expand on that. But convolutional neural networks, I just will say, are very popular for image processing, for working with images and videos. They have been used in biomedical applications, specifically cardiovascular flows. And one very interesting area is, you know that aneurysms, which are basically ballooning of your blood vessels, can happen both in blood vessels in the cranium, in your head, as well as in the various other parts of your body. And this is basically a fluid mechanics problem, in the sense that if the aneurysm ruptures due to internal pressures or whatever, then there's virtually no hope for survival of the patient. So these aneurysms are visible on imaging data, and one hope is by using the current methods basically rely on the size of the aneurysm, the age of the patient, whether he's a smoker or lifestyle, and so some 4 or 5 characteristics to evaluate the risk of an aneurysm rupture. And the hope is that by using neural networks from the fed with inputs from the imaging data, if it can predict the things like wall shear stress and the pressure on the aneurysm from the blood flow and so on, and give this data to the doctor, then the doctor will be in a much better position to make an informed judgment as to whether to operate or not. And so some of these papers deal with that, predicting arterial blood pressure from 4D MRI data using physics-informed neural networks. And another earlier paper, the second paper is an earlier one, doesn't have physics-informed neural network because I think it was not invented by the time of that study. It just uses a plain machine learning approach, plain neural network, to quickly get the relationship between shape of the aneurysm and the risk parameters of the aneurysm. A very interesting approach, and I hope somebody will be interested in this, is instead of predicting a deterministic value or one single value of UVWP at a given point, can I predict a probability distribution rather than just a value? So can I predict a mean and a variance at each point? Then I can also do uncertainty quantification along with actual deterministic prediction. And so there are separate loss functions for quantifying the mean and the variance at each point. And the following 2 papers are have used some of the more statistical approaches in physics-informed neural networks for uncertainty quantification. So basically, continuing uncertainty quantification and sensitivity analysis, because pins neural networks are very fast to evaluate. So rather than running thousands of full-fledged CFD cases, if you can train a pin, you can run it as a surrogate model for Monte Carlo and similar methods, where forward evaluations become too expensive. So one hope is that by having developed pins, these methods will become more feasible. The second thing is, the other thing is, pins have been trained to fit and calibrate unknown parameters in differential equations. So Reisi's paper talks about data-driven discovery of a physics. So that basically essentially means unknown parameters of a given equation should be can be fed. And this specifically ties in with what Dr. Shekhar Mudhu mentioned about the random fields and random field for hydraulic conductivity and the uncertainties it gives during computations, and the stochastic approaches that they take in groundwater flow. So basically, I believe that pins which output statistical or stochastic quantities will be very useful in that field. And the other case of inverse problems is, suppose you have measured data from sensors. For example, you have some concentration of pollutants under the soil. Then perhaps you can use an inverse approach using pins to see the location and the magnitude of the pollutant release in the soil. So that is one potential use of those things. So this is now, apart from CFD, there have been many other, I will mention one or two other instances of how it is being used. So one paper that I saw recently was called Deep Crash, a deep learning based vehicle system for vehicle accident and head-on collisions. So what they did was to train a neural network. Of course, not a physics-informed neural network, but a regular neural network, to sense a head-on collision using sensors, and then using a front camera, a gyroscope, and accelerometer. It detects the abnormal acceleration associated with collisions, and maybe it can deploy the airbag or tighten your seat belts and so on. And it also uses the GPS to detect your location and transmit the location of your crash to rescue services. So basically, I mean, I just thought I mentioned it because it's potentially a life-saving application. Another use in the same context was to control airbag activation. As you know, you can have a camera to detect whether a seat is occupied by an adult, a child, or some passive object, and then modify the airbag activation status, because typically I think airbags are safe to deploy only for adults. And we also know a lot of, on long trips, many times passengers assume unsafe positions like putting their legs up on a dashboard and so on. So if the airbag deploys in that situation, it can have very unfortunate results. So it can give a warning, audible warning, for you to take your leg off the dashboard, and also if you don't listen, it can switch off the airbag deployment. So again, there's a potentially life saving. Before I go on to this, let me, this actually should be case study 2. So before I go on to case study 2, let me present to you another case study. Professor Dirbude, how am I doing for time?
It's fine, it seems.
It's fine.
If you want to have a break, then we can check with Murali sir, and then
You can, why don't you check with Murali? If he is okay, then he can take over. Otherwise, I'll finish mine off quickly and he can resume later.
Dr. Murali, are you there?
Yeah, I'm there. I'm just curious at which point it went off. Because, I was trying to show some animations on the slide, and after that, I could not go into the next slide. And what I did was I got out of the PowerPoint, just escaped. Not getting out, but then I continued giving the talk without realizing that I'm not on line anymore. So up to which point?
Yeah, please open your PPT then.
What was the last slide that you saw?
Okay. Hello?
It seems we lost again Dr.
Oh,
Murali.
okay. Okay. So I'll resume then. Okay. Can you see my screen? Full screen? Okay.
Yeah.
Okay. So this is a case study one that I would like to show. Technically, actually, I missed out on the title. I should just say machine learning and the digital twin. I didn't do a physics informed learning for this. But let me. Yeah, this was the motivating example for me to get into this topic. This was basically filling a radiator with a coolant. It was an automotive application. So the problem is basically that of filling a radiator, an automotive thermal circuit with a coolant. And the issue is air bubbles get trapped in the coolant circuit during the filling process, and it can cause it does cause performance degradation under operational conditions. And my apologies, I cannot show you the original geometry. It is proprietary to the client. So I'm showing you a stock geometry, which I hope brings out the essence of the circuit. You can, in particular, I want to draw your attention to, at the very back of the thing, the radiator with a lot of hundreds of small tubes, which is where, and a reservoir sitting in the center, and a couple of pumps here and there to get the flow going. So basically, the CFD of coolant filling was being simulated by the client using 3D Navier-Stokes with turbulence models and the VOF approach. And this was very resource intensive. Each simulation, because the time step was limited by Courant number, so each simulation took place on a cluster. About 3 months or so. That's what I heard. And so when they approach me, I know that if I try the same thing, I'm going to get more or less the same result. So we had to come up with a solution to model the less critical parts. And I noticed that in the circuit, we had these radiators with very, very thin, long tubes. The flow is very, almost fully developed there, except when the air-water interface is passing through it. Once before that and after that, again, the flow is almost fully developed. So why not model those parts? They are responsible for slowing down my computation quite a bit, especially the Courant number part. So can I try a reduced order model in the sense that Dr. Murali mentioned? If I can use a reduced order model for the tubes and interface it with finite volume, then I can get a substantial savings in my mesh and hopefully speed up my result. And I would also get a performance benefit because I can march at higher Courant numbers. Okay. So I went in for model order reduction. I did a few high fidelity simulations of single tubes, two-phase flow, free surface flow in a single tube with a lot of cells. And then I tried, proper orthogonal decomposition and also DMD, dynamic mode decomposition. I did not try the last run Galeckin projection or reduced basis methods. I tried only DMD. And I did not use ANSYS twin builder. I just wanted to mention that to say that these people also have reduced order models in them. And I interfaced it with the finite volume method, but we got a good fit to the overall model, but when we interfaced it back with the finite volume, we had a lot of difficulty in maintaining the stability of the solution. It did not work too well. And in those few cases when we got a stable solution, it worked well only for those cases where you could match the original training data. It could not really interpolate too well in between them, So I then went in for a neural network. I used a version of a neural network called the long short-term memory network, LSTM neural network. This one maintains a state vector, so it's quite useful for unsteady transient models. So basically, I replaced each tube with an LSTM because the maintained state I would use a separate LSTM for each tube. And I took a single isolated tube. I used the training data that I already had to train my LSTM on that. Then I embedded it inside the finite volume code. In this case, I was using OpenFOAM. And then I had the ANN, LSTM, and the finite volume exchange data and boundary conditions at every time step. For flow, volume of fluid, pressure, actually not pressure, but the pressure gradient. And this gave me good performance improvement. It also gave me decent stability of the computations. And because of it also gave me a very decent air-water interface and flow resolution inside the small channels. And due to reduction in mesh, I was able to get a decent speed up, maybe about 30% or so. So the training data came from VOF results on OpenFOAM, and these are some details of the boundary conditions, number of runs, and so on and so forth. As you can see in CFD, it's very difficult to generate good quality training data, very expensive. So I have only 68 items of training runs. Normally, if you, a real machine learning enthusiast will laugh at the smaller data size because they usually train on, tens of thousands of images or something of data points. So I had to again do stratified simulations with only air, only water, with incoming VOF set to 0.5 and so on and so forth. So this was my basic model that I used to validate my training of the LSTM. And if we have time, I'll show a brief early simulation to show that. My so-called fine grid was not that fine, but only about 4,000 cells, but then it's a very thin and long tube. And then we map the data to a coarse mesh to train the LSTM. So you can see on the top my CFD grid for a single tube, and then I coarsen the data to fit my LSTM model too. And I'll give you some reasoning. We wanted to, first of all, this being our first experience with a neural network, and combining neural network with a finite volume solver, we did not want to bite off more than we could chew. And with the client sitting on our necks for a fast result, so we decided to make some fast approximations just to prove the concept, in the hope that the client would then have some patience to wait for a higher fidelity model later. Okay, now how did we simplify that, and why this reasoning for the kind of solution mapping to the LSTM? We went and saw the experimental data being done at the automotive company, and from the experimental data, we knew that air bubbles were not trapped in these thin long tubes. If air bubbles were trapped, it was elsewhere in the hoses and other structures. And also the flow structure was roughly fully developed. The velocity was approximately one-dimensional. All the axial gradients were fairly small, except in the vicinity of the air-water interface. But that phase is very short. Once the air-water interface passes through, then again the flow settles back to being almost one-dimensional. And the flow was almost steady because the pouring process was almost constant. Again, except when the air-water interface was passing through the individual tubes. So therefore, for most of the simulation, the flow would be either fully air or fully water coolant in the tubes, and it would also be fully developed. So then by mass conservation, the axial velocity would be almost constant, and the momentum balance would reduce to a balance between the pressure gradient and the wall friction. Again, the exception being in the vicinity of the air-water interface. Furthermore, the absolute pressure in the training configuration and the actual system are completely unrelated. You could see from my domain, which we use for training, that there will be no relationship between the pressures in this model and the pressures in a full-fledged cooling circuit. So how can you do that? If you put that pressure into the other one, then obviously you will never get a converged result. So therefore, instead of training the pressure or using the pressure in the training, we also train for the pressure gradient. Okay, dpdx, where x is the axial distance along the pipe. So the important variables in the training data were the axial velocity, the volume fraction of the coolant or water, and the axial pressure gradient. Okay, so this is basically some details of the LSTM. You have an input layer. The input shape was basically 43, which is basically 12 items times 4 variables. The axial velocity, the pressure gradient, pressure, and the VOF. So that gives me, it should be 43 internal variables. Okay. And then you pass it through LSTM. There was a batch normalization layer. Again, if you take a course in neural networks, you will know what these are. Followed by a dense layer, followed by another batch normalization, and finally you get the outputs that you are looking for. So the total number of trainable parameters were about 17,028. Okay, and we trained the model using the Keras library, but then we had to embed this model back into the solver, open form, which is written in C++. So we found a header-only library called Frugally Deep, which provides a C++ API compatible with Keras. So we just need to include the header, and then we can load the Keras train model, and then use the predict method to get the values, and then embed them back in OpenFOAM. We use special OpenFOAM functions so that it wouldn't solve the values in that zone, and just take the values from the machine learning model. Okay, so each tube again was replaced with its own LSTM model. LSTM took its boundary conditions from the CFD solution. Okay, so because it's now embedded inside the CFD code, the last 2 points of the LSTM were basically inputs from the CFD code, and then the middle points would be recycling the values from the previous timestamp. Okay, so each LSTM computes solution for its tube at each time step. Now you have to transfer these values back to the CFD code. So the CFD code takes its boundary conditions from the LSTM. So that is how we achieve the coupling. And this was found to be workable, robust, and fast. Now, what to do about the pressure? The pressure learned by LSTM was basically unrelated to the pressure. We checked it, and it was basically completely unrelated. So we could never use that one. So we took the pressure gradient given by the LSTM, and then that was put in the first and the last point as boundary conditions in the CFD code. And then once you go into the CFD code, we took that pressure gradient and used that to extrapolate the boundary pressure from its internal cells. So we use the pressure gradient information given by the LSTM to put up a boundary pressure for CFD. So a little involved, but nevertheless, I think it worked, and we arrived at this through quite a bit of trial and error process. So the interface between ML and CFD is treated like a boundary with boundary pressures coming from that. So that is my first case study, and I should have called this case study 1 case study. I somehow got it interchanged. Okay, this is still ongoing, but it's a condition modeling of a hydraulic system. Professor Dirbute, how am I doing for time?
I think it's fine.
It's fine. Okay. Okay. Good. So, so basically, there was some open data sitting in the University of California Irvine machine learning repository, And those who are interested in this is a very good source of engineering data sets on which you can practice your machine learning skills. So this is a machine learning model for monitoring fault conditions in a hydraulic circuit using some data from a few sensors. Okay. So this is the paper in which the details have been published, Helwig and at al. 2015 paper, detecting and compensating for sensor faults in a hydraulic condition monitoring system. So this is basically an experimental study where they have an hydraulic circuit and they simulate various faults in the hydraulic circuit, like leakage or pump is down or rise in temperature, flow rate issues, pump issues, and so on. And then they see what happens to what data is gathered by the sensors. So this is used to develop models for condition monitoring. Pressure, you monitor pressure, temperature, and other state variables. And they even had vibration sensors to monitor other anomalies in the system. So let me zoom this hydraulic circuit. Is it clear, the hydraulic circuit?
Yes, yes.
Is it visible? Okay.
Yeah, visible.
Okay, so you can see a typical hydraulic circuit with valves, pressure release valves, temperature sensors, pressure sensors, accumulators, pumps, vibration sensors, volume flow rate sensors, motors, and so on. Quite a few components. Now, how do we model this using neural networks? Again, we are still moving to the pin approach. We are still writing down the equations for that hydraulic circuit based on the the relationship between if you have a leakage, you have a loss of pressure, and so on. So we are still in the process of writing differential equations for those things. But in the meantime, we decided to go ahead with a purely data-driven approach to see how it works and what kind of network architecture. If you have at least a first approximation to the network architecture, then you can enhance it with the physics-informed part. So the hydraulic circuit has a lot of sensors, and they simulated 4 different types of faults. So what we did was we came up with a network architecture of whose block diagram I have given here. Yeah, okay. Oops. Can you see the block diagram properly? Okay. So you can see I've colored it. So all the pressure sensors are colored in pink. There are 6 of them. All the temperature sensors are colored in blue. I think there are 4 of them. Flow rate sensors are 2 in number. Then there are vibration sensors and some other condition variables. So one thing I should mention is the pressure sensors have 6,000 inputs because they took pressure readings at a certain frequency. I think per minute they had 6,000 readings. So we decided to try both an LSTM as well as a one-dimensional convolutional network. So what I'm showing you is from a one-dimensional convolutional network which takes 6,000 inputs. And then the temperature sensor takes 60 inputs. The flow rate sensor takes 600 inputs. And all the other variables all the other convolutional networks take 60 inputs each, because that is the output from the sensors in 1 minute. And then these inputs are passed through to a dense layer, and then the output is again split into 2. One gives the actual condition of the system, which are continuous in outputs. So basically that is a regression problem. And then there is also a classification problem which says whether the system has reached steady state or is still in transient mode. So that was a classification variable which just had binary value 0 or 1. So for that we took the output into a separate, we split the output off into a separate classification layer. So this is the overall network. It looks a little complex, but it's not really so. If you keep in mind the block diagram and think in terms of blocks, then you have the convolutional layers followed by some dense layers followed by two outputs, and you can see the pressure sensors take 6,000 inputs each. 6 into 6,000 inputs. This is the flow rate sensors which take I think 600 inputs. Temperature sensors which take 60 inputs, and other inputs are also 60 in number. And then there are two outputs which are split off from the dense layer. One is the regression output and the other is the classification output. Okay, and initial stages of training, we did something somewhat interesting. We took out the convolutional networks. We trained them separately for each sensor. We pass it through an autoencoder. An autoencoder is a neural network which basically reproduces its inputs, to a certain degree of accuracy. And in the process, it works like somewhat similar to a POD in the sense that it arrives with a compressed representation of its inputs. So each convolutional network, we train it first as an autoencoder. So in literature, it's called layer-wise unsupervised pre-training via convolutional autoencoders, and we minimize the mean square error for each sensor. And we achieved a mean square error of about 0.11%, and you can see the convergence plot of the training. So model loss started off with a fairly high value and then ended up with about 1e minus 3 or about 0.11% for the. So the supervised training is ongoing, and then the next stage is being extended with pin-based model. Okay, now I'm fairly close to the end of my my talk, so I'll finish with a slide on how to get started. You can there are a free course on NPTEL, a very good course. Part of it taught by Professor Balaji Srinivasan at IIT Madras, where he even covers the physics-informed neural network. Then there are courses on Coursera and Udemy. Of course, physics-informed neural network is not really taught anywhere in these. It's not a commercial item. It's specific only for engineering. And Google has a free crash course on machine learning. So these are good places to get started before you really get into physics-informed neural networks, which you can have an introduction on NPTEL. And you are also free to contact us at pin@acrycfd.com. So this is how you can. So my main message is it's quite the mathematics is not too difficult, and there are open source frameworks which you can use to really give you a head start. So your typical training code may be 100 or less than 100 lines of Python or something. So it's not very complicated to really get into. There's a little bit of statistics and probability and a little bit of theory of neural networks involved, but it's really nothing for those who have worked with partial differential equations and in CFD. It'll be really child's play for you to get into this area. Even if you don't do research in this area, you can still profitably use it as one more tool in your bag of tools, and is applicable in in most of the various domains from which you come. So that is literally the central message of what I wanted to really convey. And so that's it. Thank you. Questions?
Yeah, please, questions, please. So if there are no questions, let us thank Dr. Rao for his presentation, and let us move on to our previous presentation. May I request Dr. Murali to start the presentation? Dr. Murali, please.
Can you give me some time? I just want to know
Yeah.
at which point
And you have an hour to speak.
you want me to redo the whole thing? I mean, what actually happened?
You can start from the thing, but you have an hour to cover. We
Okay.
have a validatory function at 5.
Yeah,
So,
no, no. See, I'm just curious up to which point I was cut off.
yeah, there is one question in between. Maybe I think,
I
Yeah,
see one question from someone in the audience. Maybe
yeah.
Yeah, can you hear me?
yeah, I
Yeah.
can hear you.
Okay. So I'm done. So go ahead.
Dr. Rao, there is a question from someone in the audience in the chat
Audience.
box.
Okay, what is the question?
What is the difference between validation data and test data? They want to know what is the
Validation data, okay, in very simple terms, validation data is if you train one model, and test data is if you train a collection of models and use them together, then that is the in statistical terms that is the final authority on whether your models working together are good enough or not. Does that answer your question? Hello, am I audible?
Yeah, he said yes.
Okay, fine. Okay, if there are no more questions, then I think we can proceed with Dr. Murali's
Yeah,
talk.
I have a question. I just want to know at which point I got cut off.
Okay.
Because, I was actually, I have finished the whole talk, without knowing that I was cut off.
Oh, okay.
So, I would like
See,
to know.
I was capturing some screenshots. Let me see if I can find them.
I think you had just talked about the nuclear winter, and I think around that point, I think there was some break.
What about aeroelasticity problems?
No, that was not there. I
No.
think this is what you are doing. Can you see my screen? Let me share it with you so you will know which slide you're on. So this was the slide that you were on. Can you see my
Okay. So after I will go back there. Can I start from there then?
Yes, please.
Okay.
Yeah, let me stop sharing and you can.
Okay. Just give me about a few minutes. Okay. About
Yeah.
5. Okay, can I start sharing now? Hello?
Yes, please.
Yeah, right now. Can you see the screen?
Yes. Can you make it full screen?
Yes, I can. Okay, we were here, right? I mean, okay, I was talking. Can I start now?
Please.
Yes, yes, this is good.
Okay, so we were talking about this flow in a converging diverging nozzle as the first attempt at using TensorFlow and various other things. And I think the problem has been defined, and I think you lost it here. Okay, so here, this is how we set up the training data to train the neural network here. This is the back pressure and the location along the nozzle length from the inlet to the outlet, because we would like to know where the shock is formed, what is its strength, and so on. So here, the density, velocity, pressure, and energy is actually, this is a network prediction is actually sent to the governing equation to force this to satisfy these equations. And if you look at these equations, these are derivatives. So the derivatives are actually evaluated by a program called automatic differentiation, for which there was enormous amount of research done in the 80s and 90s. Basically, they wanted to estimate derivatives for design optimization and various other things. So that is being used in TensorFlow to evaluate all these derivatives. Like you can see the gradients here. These are the physics. So you can estimate the mean square error loss from the neural network, the error coming from this. If the physics is satisfied, then E1, E2, this should vanish. It should go to zero. But it will never go to zero because of all the errors and all that we have in the system. So how do you train? Okay, now here I have from a mother data set generated at 100 nodes along the x direction. I developed 27, the pressure data is developed 100 and for 27 different back pressure, because those are the inputs. And corresponding to that, I have the internal flow field. Okay, so now the mother data set consists of 100 by 27 spatial and PB variation. And each matrix will contain all these flow variables. Okay, so you have to concatenate your CFD data set into something. So we flatten the mother data set. So you have these four matrices, the vectors of size 2700 by 1, each for the four output variables. Okay, so this is how we flattened, and then from this we select randomly. Training data is generated by randomly selecting certain percentage. So this number 27 I just put there as we can change. Okay, you can have 50 or less to see how it is. And we have different points from the mother data vectors. So thus we create four data vectors of this for this. And the testing data is generated by taking spatial distribution corresponding to 6 back pressures. So that will be, so with that you train, and you can see that the comparison here. This is the pressure distribution for different back pressures. The green lines are the ground truth because they can be estimated by one-dimensional gas dynamics or even from 1D CFD code. And the purple lines you see are the ones predicted by the neural nets. So this discontinuity is where the shock is. So you can see if you just use the normal physics uninformed network, there's no physics, you can see some behavior, but it is not quite okay. But when you train it with the pin, you can see those spikes and all that are minimized, and it is getting closer and so on. Okay, although upstream there's some deviation, but we are interested in. I'm sure this also will have effect on the solution. So these two boys, they are interns from IIT Madras in the summer of 2018. That's how we got started. And they have done a lot of parametric studies like how many neural networks per layer, how many layers required, different activation functions, and so on to study the hyperparameter effect on the prediction. And so that was how we got started. Okay. A colleague of mine, Tay, extended this to axisymmetric converging diverging nozzle, where we again solve the same problem. So this is the ground truth, and we want to predict by pin and ANN, and this is the type of mother data size we have used: 1%, 0.5%, and no data. Okay, so the pin predict. The artificial neural network without any physics will only predict for the data set. When there's no data, it is useless. It cannot predict anything. But the physics, the network with the physics, even if there is no data, you can get something. Okay, so now, so this is the ground truth and this is the prediction, and you can see that how close it is. You can actually plot the pressure distribution at the wall and see what happens, but I'm not showing all that here. Then we have a case where this boundary here, that is the symmetry boundary, that has got a boundary condition. You have to put symmetry boundary condition. Okay, on the top thing, I have put the symmetry boundary condition, and that's how the. What happens if I don't impose the boundary condition? Okay, if there's no boundary condition here, then you can see the prediction. The pin is still trying to give results that are quite close to the real stuff. Okay, except you can see some kinks here because the boundary condition is missing. But the ANN gives you results that are a little bit off. Okay, so this tell you that the pin prediction is more closer to the ground truth, even for cases where the boundary data is missing. We go on to two aeroelastic problem, because this was done by PhD students at NUS, supervised by myself and my colleague, Professor Kubu Chong. And this is an aeroelasticity problem. You have an airfoil with a tank in it. Inside the tank, there is a fuel, okay? And this is a 2D tank, and this is a 2D airfoil. And this is flying at a transonic speed. And this is pitching and plunging. So it's an unsteady external flow field. And inside, there is a fluid. The tank is half filled, so it will slosh inside. And when it slosh, there will be forces on the inside walls of the tank. So how do we do this? We use a aeroelastic solver, SU2, for the external aerodynamics, and an open foam solver for the sloshing that is inside. And we make these two things talk through an interface called precise. Our experience show it is quite a difficult task to get all these different codes to talk through precise, but it is possible. You need quite a lot of work, because these are all open source softwares. They're not commercial codes. So open source beauty is that you get to do the work and you can see what is happening. So there's a certain amount of control over what. This is the equations of motion. This is the this, like the pitching and plunging pitching, alpha is pitching, plunge is edge, and this is the structural motion here. And these are the forces that act on the system. This one is the external force, CL and CM. And this one here is the internal forces coming from sloshing. Okay, so this is the net, force balance, like F equal to ma kind of statement. Okay, that's the physics. And we build a network like this. We have aerodynamic data from CFD, sloshing from CFD. And then we have a RNN. We use this recurrent neural networks. RNN networks are something like, it can, you have to feedback some stuff. So it has some memory of the past, but it does not retain a long time memory. Okay, so you need some feedback loop. So this representation of RN is like that. So you can see the time t+1, t-1, and the various variables. So RNN surrogate model for the aerodynamics and for the sloshing, and they're coupled through this structural motion. And we have two modes. First is, how do we start this aeroelastic motion? Initially, the airfoil is at rest, and we force it to move in a forced motion, forced sinusoidal motion, until the unsteady aerodynamics have been established. And after a certain time, we just let it go. We don't force it anymore. So it's a free motion, and we want to see whether it will flutter or not. Okay, so these are the two models. So there's a CFD-rich data in nonlinear dynamics, sloshing and pitching and plunging, and that's fed into this RNN network. Okay, so this networks, we use the recurrent. So here, you see the outputs of the network are the CL and CM. Inputs are the pitch and plunge, and then out here you also need to feedback input to the RNN old values of CL and CM. So that is why it has the memory part, limited memory comes in. RNN network is used for, if you look at the natural language processing, you will find that they use for, predicting speech and language and various other stuff, okay, in the computer science group. So we just borrowed it and map it in this manner, and this will predict everything inside this and that. So instead of running my open form, I should be able to use these two networks to predict that. So how good it is. Surrogate for the external aerodynamic force motion. We force it to move in a sinusoidal manner. That is the pitch. So I select some test data from this response. And so here you can see that if the apple is pitching like this, then the aerodynamic lift and moment coefficient varies like this, okay, because this is undergoing a periodic harmonic motion. So pitching like this is my CL and CM. So here, based on this response, I take a segment and use it to train this RNN network. And I can see whether the training instance, this is the training thing, whether I can predict the next instant or not. Okay, this has to be predicted by the RN. So the blue is the target and the red is the prediction. So you can see this is the CL and CM for a given pitch and plunge. And this is the training mean square error. There's no physics in this network, just pure data training. Okay. So the surrogate for the sloshing also you can do. The sloshing modes are here. This is the CFD data for pitch and plunge, and this is the lateral and vertical forces and normal movement inside the tank. Okay, so you can train them. So these are the forces coming from the sloshing. and this is the plunge and pitch, and you need the old values of the sloshing forces. So you do the thing, so you can see the target and the prediction by the neural network is pretty good, right? So that's how we build the RNN surrogate, and then we want to put the two together to see uh, whether we can have the combined aerodynamics and structural motion interaction. So aeroelastic surrogate free motion, that is, you should allow it to flutter. So the CFD for free motion, you can see that under certain conditions, the plunge amplitude will diverge, that is tending towards chaotic flutter and all that. So this one here, we generate the data from the CFD, and we take, this is the pitch, this is the plunge. The red color is the training data, and the blue is 50. So we take 50% for training, and this is the prediction. Okay, so here you can see the CL and CM prediction by the neural network, RNN, and the red line and the blue line, these are the CFD training and testing, and this is training and testing for the CM. Okay, so you can see the behavior. But if you look at the phase plot, okay, I can plot, this curve can be plotted in this direction. If you plot the lift versus the plunge and moment coefficient versus the pitch for this selection of training data, you can see the prediction is given by the yellow dots, and blue is the CFD data, and red is CFD data, CL, for training. Okay. So here you can see that in the initial period, the predictions are all good even for the moment. But as you go outwards, you can see, this is the flutter region, flutter region, you can see that the network is not able to capture the behavior quite nicely. Okay, why? Because we are using only this part to train the network, so it does not have any information of what to expect. Okay, so this tells you about how you select. So you don't take training data continuously. You should have taken randomly, some from here, some from there, and then when you do that, the prediction will be better. So this is basically to show that point of how you select your random, because you have a lot of data sitting there. How do you select it? You should do randomly, and the way you select the training data will affect the prediction. Okay, because for a thing like this, you can see that. In the sloshing surrogate motion, you can see the predictions are here. The forces, forces and moment, seems like it does a pretty good job, the surrogate. And you put everything together, aero, structural, sloshing, RNN, all by RNN, the CL and CM prediction, and the plunge and the pitch. Okay, so the surrogate model and the couple CFD. So this is how the predictions are there, except for the maximum amplitude. Some things are not there. So we have reported this in an archive paper here in 2019 November, and we haven't added any pin here, but you can look at this, and if somebody is interested in adding some additional work, please let me know. I'm willing to work with them on that. The machine learning algorithms are all implemented in TensorFlow. Okay. The other thing we have done is the deep learning based non-linear reduced order model for transonic airfoil Gus aileron bus response. Are you guys still there? I just have to check whether you are still there, or
Yeah,
if my
yeah,
network is still, if
yeah.
my network goes, please send me a message or something. So here there is a airfoil, there is a hinge there, and there is a flap. The airfoil is just not moving; it is just, but this hinge is this flap is free to move. So as a gust is there is a transonic flow, external transonic flow, and we superimpose a gust, okay, which goes, the gust is a vertically rising air, and when it goes over this airfoil, this flap may start to move, and so the motion of that flap is controlled by this angle beta, okay, which is given by this moment moment of inertia times the second order different derivative of the beta is equal to that torque. All right. So here is the same equation. We solve it in SU2. This just do a Euler. So this is a Navier-Stokes equation. Okay, viscous flow, everything in SU2. So this is the equations for the structural equations, and this is where the aerodynamics coupled with the SU2. Okay. So here what we do is we're not going to trigger a response using sinusoidal motion, but instead we use a random. So the gust velocity is a random. Okay, there's a free stream velocity, there's a gust velocity. And these are the responses of the computed responses of CL, CM at beta, and CM of the hinge with time due to this signal. So if the airfoil is subjected to this type of gust signal, then these are the responses. So these are the data which I'm going to use for training. Now, if I'm using LSTM here, and I don't think I need to talk a lot about LSTM because Professor Madhukar already talked about it. So here, I'm using a reduced order model, which is called discrete empirical interpolation method, DEIM. Okay, and I couple it with a LSTM to address an issue we face. Because if you look at the ROM, our equations, our differential equations, even the discrete equation, if we look at, is actually like a first order ODE. It is written in this form. It is nonlinear flow equations. Okay, so if I use a linear ROM, and if the Mach number is, say, the low transonic regime, like 0.7, I have no problem. The linear ROM perfectly predicts the behavior. But when I increase the free stream Mach number to the transonic regime, like 0.854, I find that the linear ROM does not predict the outcome correctly. You can see this whole prediction is different, the CL and CM. You can see the high fidelity result is this one, but the prediction from the linear ROM is that. So linear ROM does not appear to work poorly. Reason is very simple, because at this 0.7 Mach number, you don't have any nonlinear phenomena happening in the vicinity of the airfoil. In the case of a transonic flow like 0.85, it is really a nonlinear flow. So you cannot expect a linear ROM to predict. So we need to go to the nonlinear ROM, and that's what we considered. So this equation actually is projected onto some port basis, and then we get a compressed discretization, reduced compressed form of the high dimensional nonlinear function, which we are interested in. Okay, the details of this, you can read this paper by Chattarun, Butt, and Sorensen. Came out in 2010, and the first application was in a flight dynamics problem. So to do this non-intrusive ROM, okay, so there is intrusive ROM and non-intrusive ROM. Intrusive meaning when you do the ROM, you have to go into the code and do a lot of changes. Okay, non-intrusive, you don't have to do that. And the non-intrusive is based on machine learning. So what we do here is you have a snapshot of flow variables under training gust input, various training gusts we generate, and we locate the DAME control points and get the DAME modes, and then feed it into a deep learning network.
I think we have lost you. Murli sir?
Hear me?
Yeah, now you're audible.
You can hear me now?
Yeah, yeah.
Okay, so I continue, okay? Can you see the slide? You have seen this slide before, right?
Yes.
Okay. So once in a while, they would just give me, say, after every 5 or 10 minutes, so 10 minutes, just give me some sound,
Okay. Yeah.
huh? So that I
Yeah,
know that
sure,
you
sure.
guys, yeah. So this is the LSTM network, okay? And here, if you look at the LSTM network, this is a block there. This block has got some internal stuff inside. It is not like a normal stuff. It has got a input gate, output gate, a forget gate, and all that. And there's a small network inside. And this M here is a memory. There's a long short-term memory can actually store a lot of old data. So it has got more memory and it's much better than RNN. So we were examining these two networks during that period when both students were there. And what we found, so this is LSTM. There's no pin here again because we just wanted to find out. So here, the problem is, again, the output from the old time must be fed into the current time. Okay, so it is all connected. Okay, so you can see this red line here. So this is the prediction here at YT, but it depends on the output from the previous time and so on. And this guy depend on the next and all that. So it's all connected. So that is why it is called the long short-term memory. And inside this network here, you can forget some data if you think it is not interesting. So that's how it will move, right, to the next level and so on. Okay, so you have many layers of LSTM, and that's what. So you have two LSTM. One is to construct the global variables. By global variables, I mean the aerodynamic force and moments. Okay, and the inputs are the structural and gust input. Okay, we already know the signal, so we just put it in. And the other one is the LSTM for the reconstruction of the distributive variables. So distributive variables means I want to know what is the flow field, what is the CP distribution on the surface of the air for skin friction and all that. So that input, structural input and gust input you put, I should be able to predict all that. So there are some layers you can play with it. We haven't done the parametric studies. They just demonstrate the concept. Okay. So you do that.
I think we lost you again. We lost the connection with you, sir. Murli sir? Sir, you are not audible, sir.
Are you able to? I think you can see now, right?
Yeah, now you're audible, sir.
Okay, I have to share again. Is it?
Yeah, now.
Okay,
Yeah,
let me
you
share.
can start with this same slide.
Yeah, but I share again. Okay. I think I keep it like this, huh? Is keeping the slide like this okay, or you want full screen? Can you hear me?
Yes, full
Yeah,
screen.
yeah.
Full
Full
screen.
screen is better, sir.
Okay, I change a different line. I use a different network, So I don't know when that. Okay, here there is we use 15 modes. 50 neurons, and the EPO, this is the loss function, pin loss function, for predicting that network parameters. We use ADAM, we use hyperbolic tan activation function. Neurons, we use 50, hidden layer 4, and mean square. So there's no physics yet, but physics we are trying to add, and we will show you some. So if you use the DAME LSTM approach for the nonlinear case, that is at high Mach number, you can see the prediction of the aerodynamics and moment, which was poorly predicted by the linear ROM. The nonlinear ROM coupled with the LSTM network does a pretty good job. You can see that. Okay, so and you can also reconstruct, because you have all the information, and you can reconstruct the flow field from the predictions. So that's how it looks like, and you can compare. All right, this is the actual Mach number, this is the reconstructed flow field, and this is the error. The maximum errors are where the shock is, because this is where the shock is. So this is the combined gas and structural response under a sinusoidal impact. So if you want to see more about all this, you can look at our paper, which just came out in October 2020. And if any of you are interested in pushing this further, please let me know. We are actually now in the stage of trying to put a pin in the LSTM. And what we do is we just test it on a structural thing, initial attack. That is, this is actually a point mass. Effort doesn't make any difference. So just pitching and plunging, and you have the structural equations. Here I have F1 and F2. By right, they are different, but for this test, I'm assuming it to be the same. So the signal that I'm going to give is a combination of random input and sinusoidal input. Okay, so this is the signal for F that I'm going to feed into the system, and then I look for the response. And from the response, I will train the LSTM network, which is this one here. And the output that is coming out is actually put into the physics network. The physics is this equation here, the structural response, because the outputs are H alpha, H dot, and alpha dot. Because this second order derivative equation can be converted into a first order, so you have an expanded system. And that gives us this system here we want to predict. And if you add a pin to it, you take this output and put inside the pin, which is the differential equation here. So this is the uninformed, and this is the physics. Okay, so here we do this in Keras. Apparently, when we were evaluating the automatic different derivative formula in Keras, we ran into some issues. So we write our own for this, because it's quite a simple case, and that seemed to work. So if you take 50% of the data of the training excitation randomly, and then the entire test date, and the rest is all, entire test date is, you want to do how the prediction is, okay, based on the data. So this one here, the black line is the ground truth and LSTM. So this is the prediction just by the LSTM only, no physics. So you can see, the purple, you can see some overshoot at the maximum amplitude of alpha. And here we use the LSTM pin, because you also have the error from the physics, because it's being fed in, X is fed into the equation, and the error is computed and coupled with the LSTM network error. And you can see that the prediction is very good compared to the ground truth. And if you take 3% of the data, and you can see that the LSTM prediction is pretty bad. You can see the black and red. because I have less data, but the pin does much better. And so this is the L2 norm without pin, with pin, and so on. You can see the L2 norm for these variables during the prediction. So the pin actually requires, if you use pin, what it tells us is you may not need that much of a training data to get the prediction of the. So this one here is a PIV data from my colleague Yongdong and Razak. They are experimentalists. Suppose I have PIV data. This is very similar to what we talked about earlier in the pod, using the example from Professor Weiss. So how do you determine the pressure field from the PIV velocity data? You have, so you can put a grid there, and the PIV has a lot of velocity information. So you can actually solve either of this equation. Okay, numerically, that is details you can see in this. Or you can use a flow pin to estimate the pressure. You can use, wait a minute. Can you see? Can you still see? Hello?
Yeah, but full screen will
No.
be better.
Huh?
Full screen will be better, sir.
Yeah, but I don't know why it's overshooting, that's okay.
Your voice is now breaking.
Oh, never mind, I just moved. So now it's okay?
Yeah.
Okay, so you can take the velocity field and put it in a pin, like what Marisi and the Brown group has done, and predict the pressure. Or you can use the one without any data, without any training data. You just put the inputs and the boundary conditions and the governing equation using auto differentiation in TensorFlow, and predict the stuff. Okay, so that is two approaches one can do to handle this. Now is the problem. When I go to the next one, I need to wait a minute. Let me flip. This one is actually an animation, and this is a case of lid-driven cavity where the top lid is actually moving back and forth in a sinusoidal manner. And this is the CFD prediction, ANN, and PIN. Okay, so if you predict, this is the animation of the P, U, and V components from the three cases. You can see that the PIN prediction closer to, it's very difficult to tell, but I think it depends on a lot of so this is actually using the training data, and these are the MSE and the physics residual convergence. This is the spatial distribution at a particular instant of time. Are you still able to see the screen?
Yeah.
This is the last bit. We are also exploring surrogate this machine learning in the field of aerodynamic design optimization. So like what we have been doing earlier is you have a given airfoil geometry, and there's a need to optimize certain objective function, like maybe the shape function with some constraints and so on. So what you do earlier on, what I have done is we generate the CFD solutions from the CFD code to construct the objective function, which is actually optimized by an optimization algorithm. It can be genetic, it can be gradient based, hybrid, or even simulated annealing. We have done all that. And then you get a new variable, then you have to regenerate the geometry and go on in a cycle. So this is a very expensive affair. So we can knock this off by building a surrogate and train a neural network to predict the necessary things that are required in the objective. We have a problem here with the flap setting. You have an airfoil with a flap, and there are 4 design parameters: gap, flap, and overlap. And for a angle of attack, objective function, now to maximize this thing, this is the endurance, and there'll be constraints, so I need to maximize the objective function with the constraints. So the neural networks box here will be trained with the CFD data, and then after that you initialize flap and these parameters and train. You get the CL, CD, CM, whatever. You compute the loss, and optimization done using some of the packages that are available in TensorFlow, L, BFGS, B, whatever. So some work we are doing with the MSCS as the CFD code, and we train the neural network with hyperparameters and everything. So this is the MSC versus the training EPO with different sets of values of the hyperparameters, okay, like layers, number of layers of, and so on. And this is the training sample, validation sample. We want to see how good the MLP ANN model is using the TAN activation. So it's the spread. So what we do is we put the predicted CL and the true CL and see where it lies. So if it lies exactly along the 45-degree line, then it's okay. The spread will tell you the error in the prediction by neural net. So this is the aerodynamic characteristics, okay, predicted by the neural network and compared with the MSC. All right. So they are in.
We lost you, sir. Lost
To
the
do
connection,
some
sir.
tuning. Now, for those of you interested, you can actually take.
We have lost the connection, sir.
When I'm about to finish already. Wait a minute. How about now?
Yeah, fine. You can make your PPT. Yeah.
Yeah.
Presentation gone, sir.
Yeah, I know. How about now? Can you see?
Yeah.
Okay. So there is a group at.
You can make full screen, sir.
Yeah. At Argonne National Lab, Romit Maulik, Sharma Patel, they developed something in TensorFlow and OpenFOAM combined together called TensorFlow Foam. And the paper, basically, they try to use OpenFOAM to generate the results and couple it with TensorFlow. This is a good initiative. It is in Computers and Fluid. It's online. Okay, it will be published very soon. And here is the code. The code is publicly available. The paper is at this site. If you cannot access this, you can try this. Okay. So here, Himanshu Sharma was one of my former MTech students when I was at IIT Gandhinagar. So this is a good start for it because you have a platform which is OpenFOAM, develop the CFD solution, and TensorFlow combined together. So although this is for one particular problem, which is a backward-facing step, I guess once you get a hang of it, I think you can actually extend it to any problem of interest. Okay, so it's worth trying for you guys. So this is the current state, as predicted by that scientific machine learning thing. this is going to take off. As you can see, the talk given by Dr. Madhukar, he was talking about a lot of things he was doing with the hydraulic systems and so on. And that is what we are aiming at. The digital twin building is what we are all after. And definitely that is not going to rely on high fidelity CFD simulation. It is going to be built using the reduced order model and the physics informed. So the job is, what is happening now is to see what is the quality of these surrogates, whether they can really function in real systems. So surrogate building using machine learning is happening across the world. There are people across the disciplines, like flight controllers, they are using reinforcement learning and so on. So this is and if you couple this surrogate simulations and physics informed stuff with virtual reality, there you have it, So this is the current trend. You can read this. This figure is from this article. You can read this journal. That's all I have to say. Hello. I'm done.
Yes, sir, we can hear you.
Thank you, Murali. That was very nice.
Yeah, I saw it. I heard all your slides. I mean, all your talk as well. Very interesting problems you guys are doing. Hydraulic systems and all that is. I want to follow it up with you after.
Well, we are doing a lot of hydraulic things together.
Yeah. Okay. So that's the state for new activities, which some of the younger people in the audience should probably consider venturing into. All right. Madhukar, you want to say anything on that?
Yes, I think I think on a bottom line kind of thing, we are ready to give a hand to anyone who wants to use these techniques in their work. That's the main point I want to make again. There is also a nice LinkedIn group for PIN. Started by Karnataka himself. I think those who are interested should join that LinkedIn group also. But I think in India we should form a separate group of our own just to discuss problems of mutual interest and throw ideas back and forth and so on. I mean, the field is just starting up, and this is the best time to enter a field. Right?
Yeah, I fully agree with you on that. And I think you need to engage a lot of people.
Yes.
If
you wait another 10, 15 years, it will be a mature discipline, and then
gone.
The fun is gone from that.
I got a feeling the fun will be going off very soon.
No, not. I think we are good for another 10 years at least.
Yeah.
Because there are so many different applications. You saw the one on automobile crash testing.
Yeah.
And, I think it's quite a thing. I think some of the tsunami modeling. You can have near real-time prediction of tsunami from buoys in the ocean and all that early warning systems. I think I think we're going to see a lot of activity start up.
Okay. Any comments or questions from the floor? Or is it done?
I think we can take some questions. I think we have still about 5 minutes at least. Please feel free to ask questions, because we know that most of you would not have had exposure to this topic. Must be a first time for everyone.
Okay, never mind. My thing. I think let's hear from some of the younger people in the audience what they feel about the topics that we presented today on the sort of models and machine learning in fluid dynamics. Whether we just want some feedback from the younger people in the audience, what they think about it.
Sir, good afternoon, sir.
Yes.
Sir, it's regarding a doubt, in PIN, the outputs of ANN are given as initial guess for the governing differential equations.
Yes, you see, because we are solving the Navier-Stokes equation, so the outputs are the flow variables P, U, and V for 2D flows, and the inputs are the gradient. I mean the locations X, Y, T, because that's what we want to find. Okay, that's just one aspect. Okay, so if as long as you have a output which is flow variables, you can put that in the governing equations because we know that P, U, and V has to obey the physics. So if you put the values of P, U, and V, which is predicted by the neural network, if you put it in the differential equation, it will never be satisfied. I mean, in a sense that it won't be zero. Okay, so there will be an error there. So you collect all that error and couple it with the MSE, because you see that what is being fed your U, V, and P is dependent on the weight. You have a functional description between the input and the output. So it is going to depend on the weights which is being optimized by the MSE. That is implicit in the U, V, and P. Okay, these are not numbers you're talking about. It is actually a function. The functional form, which I think both of us have shown. It is a very complex function, which actually can be something like spectral method, that for finding the solution in the space. And that
Sir, means the
from the
function.
physics, you put inside the MSE and optimize it together. So that will improve the pin prediction.
Sir, means the functional form is given as input for the governing differential equations.
No. You see, if you look at it, I can show you the functional form. Okay, let me put my slide up. Just a minute, huh? Okay. Okay, let me. Can you see? Can you
Yes,
see
sir.
this?
Yes.
Okay, so you see, I have input X and Y. Huh? Okay, this is the function. See, Y is actually the activation function operating. It's a very complex function, and X is here, the input variable. So your U, P, and V will have all these weights inside, and that is what is going inside the physics. To get that physics error. So that will go inside your automatic differentiation tool in TensorFlow, and you will get the effect of all the weights, everything. So that is why when you add that error into the MSE, the non-informed ANN, okay, so the effect of the physics is already included in the optimization. Is it okay?
Yes, sir. Thank you. Yes, sir.
I think I see a new question. How is CNN different?
Um, I actually don't use CNN at all. CNN, right? Convolutional neural network. Yeah, that is usually used for image processing and all that. And some people have used it for CFD, but I am trying to understand how that can be used.
Yeah, well, I think just to add to that, convolutional neural networks are sort of useful when you have very large input, and if you use a dense layer, you would probably run out of RAM on your computer.
Yeah.
So you
No,
use that.
I've seen some work by people using CNN for aerodynamic flows and so on.
Yeah.
I think Karthik group in
Yeah.
Michigan has published some papers on that.
Yes.
Yeah.
So for example, for that hydraulic system, I had
Yeah.
6,000 into 6 inputs. I mean, if
Yeah.
if I take 36,000 numbers into a dense layer, and then I have to keep reducing that, then I had problems with RAM and all those things. And besides, that level of high dimensional inputs is usually you can try to compress it into a very sparse, it's usually a sparse data, and you can do a lot of compression on that. So CNN is useful to achieve a sparse thing because so many of the inputs share the same weights, so you don't have to store all those weights
Yes.
in separate numbers. So that's how to explain it a little more, we'll have to draw some pictures. So it's a little difficult to explain purely using text. We'll have to do some pictures. Just think of a structured grid of numbers, and you run a small, you take a small portion of that as input at a time, and then you can run the same input on all the pieces of that structured grid. So that gives you a better pictorial idea of how that is. I think for more than that, we'll have to go into we'll have to put up some pictures, which currently I don't have.
There seems one question from the Balminagam. How is CNN different?
No, we addressed that.
Okay, that's good. So, any more questions? So, if there are no questions, we thank Dr. Murali for giving nice presentation. Now we are at the end of, we just finished our short-term tennis program, and now we will start our validity function. So over the period of this 5 days, it was a very interesting and tight kind of, with a lot of learnings from various speakers on different topics, and hands-on sessions were found to be very useful and effective, and much more response was there from the participants. Thank you to all the participants who came from engineering colleges as a student, 34 participants, and 7 from faculties from various institutes, and 10 from industries, scientific organizations. So thank you for their patience listening and giving time, and has showing good interaction with the speakers, and we hope that we have succeeded in our goal in giving a short-term training and giving a training on modern CFD to few of the groups in India. may I request some of the participants, if they wish to speak upon, they can share their words. Any participant would like to put views?
Dr. Sumer, it can be some of their suggestions also if they find any to be improved, because we welcome almost all criticisms, constructive criticisms, so that if anything has to be improved further, we are ready to do that. Please ask them to do that also.
Yeah. And also in a chat box, we have circulated a Google form for your valuable feedbacks, and also we'll send you that link through your emails. You please give us your valuable feedbacks so that we can think for a better arrangement and organization of another short-term training program, which will be much more better with your inputs. So anybody who wish to share their views can please share. Any suggestions they have in terms of the course content, please feel free. Yeah, you can switch on your mic. Jaya Kumar sir, can you please switch on your mic and just have interaction, just to hear from you.
Sir, good evening, sir. This is Jay Kumar and overall BEML team. We are here. Hello, can you able to hear me?
Yes, sir. Yes, sir.
Yeah. This session was very nice, especially theory session and all very nice. Actually, we are from industrial background.
Yeah.
Actually, one of the problem statement already we forwarded to your mail ID.
Yeah.
Further, we need your assistance also in that.
Yeah, sure. We'll look into it and we'll get back to you.
Yeah. Further sessions, if industry related any issues, if you willing to solve, it will be very good for us, especially.
Absolutely.
And particularly turbo machinery problems we are interested in for solving for our practical industry applications. For example, gear pump applications.
Okay. Yeah.
So we are having software fluent and star CCM we are having actually. Both software we are having already. So we are solving like hydraulic torque converter and hydraulic pump and all we are using. We are solving. We are facing some issues in that. So if your technical assistance is there, it will be very good for us.
Yeah, sure. We can think from in that direction.
Yes. Thank you, sir. Thank you. Thank you to all.
Thank you to all, sir.
Yeah.
Thank you.
Nice.
Thank you. Well, it's my pleasure. Dr. Mitra, Sudeep Mitra, will you please say a few words? Dr. Mitra, are you there? Dr. Prashant?
Yeah, good afternoon.
Good afternoon, sir.
Yeah, we as a team from NPCL has attended this workshop. Some of the people are working in CFD application areas using commercial softwares, whereas some people are interested to develop their own software. But most of the issues like estimation of flow feed or temperature are very much essentially solved by the very high level accuracy by the CFD. But some of the areas which we are looking into are like hydrogen detonation, then atmospheric dispersion with the various air stability criteria, then tsunami simulation and associated wave heights. These are some of the recent topics that have started gaining interest in the people, and we are looking forward to get more insight using some commercial CFD softwares or developing our own assets for that. So this workshop was very helpful in that respect, giving new insights. Also, some of the newer methods that Professor Prabhu taught, like SPH, and the recent topic today, like ANOS, was very helpful, and it has given new insight to thought and develop a thought process for us. So it was a very encouraging workshop, and we gained a lot through this.
Yeah, thank you, Dr. Prashant. May I request Bharti Prasad, MS Bharti Prasad, Miss Bharti Prasad?
Yes, sir, am I audible?
Yeah, please.
Yes, thank you very much, sir. It was a really nice session, all especially hands-on, because before hands-on, the theory of the software and the problem statement were very, very fine. So it was very usable.
Can you please
The only thing
tell about
I
your
felt was,
institute?
yes,
Excuse me.
pardon,
Can you
sir?
please tell about your institute?
Am I
Where are?
audible, sir?
Yeah. Please tell about your institute. Yeah, you're audible, ma'am.
Am I audible, sir?
Yeah. Yes, ma'am. So, Professor Bharti is from
Yes,
NITE Meenakshi Institute
am I
of
audible,
Technology,
sir?
Bangalore.
Your
Yeah,
voice breaking is there.
yeah. Please, Bharti ma'am. Yeah, please, Bharti ma'am.
Yes, sir, yes, sir. And actually, I think network issue was there. So I really like that hands-on session. As I was telling that before the hands-on session, the process, all the problem statements were defined very well. Even there was one complete session before each software was there to explain about where to what is there. So while we were doing the hands-on, the flow was there. It's not that first time you're seeing the software and parallelly you're solving. So that was very good. The only thing I felt my background is civil engineering, and I specialize in hydraulics. So I know CFD, but I'm actually not working in CFD. So it was little higher side on for me to completely understand the problem statement. But at least I know many, especially this artificial neural network and machine learning, that these can be or CFD problems can also be solved through these, because I do working on artificial intelligence, but was not aware that even CFD can be so effectively applied through machine learning. So it was really good to know these things. I'm really thankful, sir, for the overall session.
Thank you, Bharti ma'am. May I request Dr. Sushil Bhandari to say a few words or there any feedback he has? Dr. Sushil Bhandari.
Hello, everyone. Are you listening?
Yes, sir.
Okay, so I feel this is a very good workshop, and especially the talks on turbulence modeling 1 and 2, and artificial neural network, as well as some tsunami modeling talk I like very much. So it covers it gives an idea about basically some important ideas about on research topics, so that one can build the things. Overall, it is a very good good workshop, and lectures are very interesting.
Yeah, thank you, Dr. Bhandari. Dr. Bhandari was from GB Panti Nagar GB Pant
Pantnagar
University.
University.
Pantnagar University.
Yeah.
Yeah, GB Panti.
So,
May I request? Anything, Dr. Bhandari, you want to add?
can we get, sir, topic of these means lecture notes or slide of
Yeah,
these?
all these sessions were recorded, so I'll just edit the recordings and I will distribute these recordings.
Okay.
That should be fine, I think.
Okay. That will be fine. Okay.
So we'll take up some of the students, I think. Debashish Ghosh, Mr. Debashish Ghosh. Debashish?
Yeah, yeah, sure.
Yeah, please.
Yeah, it was a very nice session. I'm new in this field. I'm started working in this field and learned a lot of things here. And the hands-on sessions are really nice. Learned that each and every software very well, like Answer and Tidal and all those things. So it was really nice. Nothing to add anymore. Thank you all.
Uh, Mahesh Pandey, can you add some? Mahesh Pandey?
Yes, sir. Uh, Thank you, sir, for this nice whatever I got from this event is very much because lots of software skill developed by this event and lots of extra means, lecture I got from the different professors which are very much experienced. So this add our in our research this add extra and we can just to focus on these things to add some extra in our research area, sir. Thank you very much, sir. Thank you, sir.
Thanks, Mahesh. Rahul MMC from Coimbatore Institute of Technology. Rahul MMC. May I request Dr. Arvind from NIT Calicut? Dr. Arvind?
Sir, am I audible?
Yeah, please.
Okay. It was a very wonderful session, all the 5 days. I could not attend all these things because of my class and all. Still, the hands-on sessions was very wonderful. Learned some new softwares, and it was overall a very good training program.
Okay, thank you. Amulya is there? Amulya? Amulya? Deepak Kumar? Yeah. Amulya is there? Amulya? May I request Nitesh Kumar to say a few words? Give us feedback. Nitesh Kumar? Dr. Rajendra Prasad Soni, do you want to add something?
Sir, am I audible now?
Yeah, please.
Yeah. Sir, actually, like due to the because I had some classes, so because of that, I had not attended all the sessions. But actually, I had attended sessions related to turbulence flow, and actually today all the sessions, like almost all the sessions, I attended. So I like the sessions related to turbulence modeling. And today, actually, this topic presented by Professor Prabhu from IIT Bombay. The topic related to that actually I like the most, and also related to this machine learning topics. Actually, these things are new to us, but actually because the application of this machine learning are now developing, so I slowly actually I developed some interest in this machine learning topic and application of this machine learning in CFD. So overall, it was a very nice experience, and actually it was a very nice workshop. Thank you.
Thanks a lot. Anybody who wish to speak, they can please. So regarding the certificates will be distributed after this program through emails. Now, before we conclude, I thank Dr. Jose Matthew for giving this opportunity to me. And when I asked him about this 5 days program, he was very enthusiastic in giving me a permission to organize this and help me at various levels. And also thank the team behind this, who were eventually our speakers in organizing this event. So I'm obliged to all of this, and I would request now Professor Jose Matthew, our head of the department, to say a few words and conclude the short-term training program.
Okay, Sumir, before, how many are final participants? The numbers, you not read the names. How many numbers were there?
Okay, I'll read the names.
No, there's no need to read the names, you just read the number.
34 student participants, 7 faculties from the academics, and 10 from industries.
Okay, fine, that's enough. And we have the experts. How many experts? Around a dozen experts were there.
We have 12 experts.
Okay, fine. Okay, that's fine. Okay. So let me come to my duty. I was listening some of the talks. What I observed is, first of all, thank you all for attending and taking this much care. What I have noticed is, online we are arranging maybe for the first time like this. Normally for this workshop or FDP programs, people are coming to Kerala for mainly 2 reasons. One, maybe for learning, real interest. And we have seen sometimes the other side is also that is they are taking this as a visit, coming with family, see the place, go around and all. And what I have noticed, this program, in the sense, the experts were highly devoted, highly competent people, even from abroad. And more than that, the participants are all equally showing that much interest, highly motivated, and I could see most of the participants are there throughout the program. That's also a very positive note. And I'm sure that this might happen because of the efforts taken by Sumir, and he could bring all the people, eminent people in this field, and this short notice time. And it's very happy, and I'm proud that mechanical department could able to do something for the benefit of people on the CFD areas. And sure, we'll continue such programs in future. I thank once again Sumir for taking the efforts to arrange this beautiful program. And we'll definitely keep on arrange similar programs in our future, because we have very good colleagues with me. That's what I feel proud that. I always said NID Calicut Mechanical is one of the best. We have good people, faculty as well as students. So let us try once again and again. Another thing what I notice, industry people, they are also very much interested to solve their industry problems, because it's up to your title also. That's one area I think we have to look at in future, how more collaboration with industry. And even now what we are thinking is, even some of our students problems, that is projects, MTech, BTech, or even PhD problems, if we can link it with some of the industry problems, that that will be more beneficial both for the industry as well as for academia. That also we can think seriously, and we have got very reputed companies who participated this session. Sumir, you just see that what all collaboration we can build up with them, and so that we can work some joint collaboration in that area.
Sure, sir. Sure.
And it can be even some, that suppose, as I said, as that our electives, suppose that electives, some of these eminent people can give some short talks, 1 or 2 hours or 3 hours, part of the program. So we can make it a collaboratory with the industry or institute, or what of this or now. So let us have that culture so that it will have more practicality in the picture, and then it is a real life situation. People also will start enjoying that rather than simply seeing the theory. I think that also we have to think. We have already started that work. We are already going to start some MOUs with some CMD and ARCI, Hyderabad, the near future. And similar things also you can try with the industries as well as public sector companies also. So I'm sure that this will be a good beginning for that. And I congratulate all of you for successfully participating, and your feedback itself tells that you really enjoyed it. It's not for fun you attended that, to get the real experience. That's good. So keep on continue that your learning, because learning is a continuous, it's a journey. So there's nothing like we stopped it and all. CFD, APM, like that. It was. I also had when I did my MTech in 84 at 90s in IIT Kanpur. But you know that now that is entirely different. New developers, new ideas are coming up, and it's a very emerging tool. And as I said in the beginning, NIT Calcutta, we offer these courses part of our BTech PG electives, so that we are in line with what's actually going on in these emerging areas. So with this note, I thank once again all of you for participating, and come to Kerala whenever you get a time, maybe after the COVID time. Normally the FTP workshop time, you know that we always ask them to see our place also. One day we may spare for go around the place, see the beauty of the Kerala. So whenever you get time, please visit NIT Calicut as well as Kerala. We call it Scots on country. Now it's not possible because of Corona. Hope so that will get controlled soon. Okay. I thank all of you once again, and have a nice weekend. Thank you.
Thank you, Professor Jose Matthew, for your advice and your sharing your vision with us. And we will try to follow your vision, and we'll do the best possible which we can do. So once again, I at the end, I would like to thank all the participants, all the speakers, and the team behind organizing this, for making this program successful. And hope see you soon. With this, we conclude this session. See you all.
Okay. Bye.
Bye bye. See you all.
Bye.